那我们今天开始上课哦。Okay, now let's start the class. So originally we were scheduled to have quiz 2 on the week of the 5th week. So it's going to be next week. But we are a little bit fast actually. We are going through the second part of bounding concepts, and I think we'll finish it today. But we'll see. We'll see. Don't worry. And we'll see if it's a bit hard to choose. Should we actually go beyond to going to covalent bondings? That means we're going to have more stuff in the exam, or we're going to just be slow and finish bonding concepts. Any preference? 好，那我们就讲一遍了。好，那这两个上的稍微比期程来的快一点，所以呢 ，bonding concepts 大概在这个礼拜应该就会教完。那也就是说 ，quiz 2应该会早一点，那没关系，我会提醒你们哦。那 officially 这堂课我们是可以把 covalent bonding 先读，那也就是说 exam 1会有稍微比较多的内容。当然，我相信这大家应该是最不喜欢看到这个结果。那我觉得问你们，大家都说，那我们再教慢一点。好，那没关系，我们看一下我们今天这堂课教的速度好了，因为没意外的话，我们今天 bonding concepts 应该就会上完。If they are less, bonding concepts should be finished today, so we will see. Don't worry about that. And if we finish early, I'm going to remind you that quiz 2 will be opened earlier. So, yeah, and I will remind you. Don't worry. Okay, that's a slight schedule change, but we will see. All right, let's finish bonding concepts today. All right, so we're going to continue into the survey of bonding concepts into the remaining part of the ideas, which is the more advanced level about bondings. And of course, bonding is a really hard topic, right? It doesn't just stop here. It goes beyond and still under debate nowadays for some special cases, right? So we're going to learn about a really simple description of bondings, right? So localized electron bonding models, assuming that electrons are just pairs, like within a bond. But of course, we know the electrons can be fully delocalized, right? And we can also have resonance structures like that. And then, how do we actually come up with localized bonds? We have a more general idea called Lewis structures, right? And then later on, we know that sometimes we have resonance, like in benzenes, where the high bondings are actually locatable in the whole ring. Then we know that localized electron bondings is actually not the correct model. It's really oversimplified. And then, of course, then we go into, we use resonance as a way to say that localized electron bonding model fails actually a lot of times. And of course, in addition to that, Lewis structures can also fail, right? For example, the exception to the octet rule. Right? Lewis structure assuming that all you need to do is to fulfill octet rule. And later on, when we go to a third rule and fourth rule and so on and beyond, we realize that octet rule just doesn't hold anymore. And lastly, the major goal of the whole bonding concept is how do molecules look like, right? So overall, we'll come out to something called the Vesper model. Of course, it's also an oversimplified model, right? All right, so last time we stopped here, right? That means last time we realized that to calculate the energy of bonds of a whole molecule, we can actually have a table of the energies of bonds, right? Hydrogen-hydrogen bond, carbon-hydrogen bond, carbon-carbon bond. And for example, for methane, CH4, all we need to do is to take this energy and multiply by 4, because we have 4 CH bonds. And how did we come up with this energy? All we need to do is take methane and just burn it, right? And burn it will create carbon dioxide, but you can also burn it in an atmosphere, which you can potentially generate with a very dilute environment, potentially generate carbon and hydrogen dots. Right? Of course, it may not be that simple in experiment, but then you can measure the amount of heat released or amount of heat required to break the bonds, and then you divide by 4, basically. Right? And then with this table, then you can actually calculate the energy change with an experiment, with any reaction, just by taking enthalpy change of any experiment by taking the sum of all the bonds broken minus the sum of all the energy bonds formed, right? To break a bond, we absorb energy, hence it's positive. To form a bond, we release energy, hence it's negative, right? For example, H2 and F2, we are breaking HH, breaking FF, and forming 2HF, right? So we're going to sum up the energy of the bond formation enthalpy of HFF Just from looking at this table, HH 432 and FF will be somewhere here, 154. So these will be positive, right? 432 and 154, and we're going to form. So we're going to minus 2HF. HF is here, 565. 65 multiplied by 2. So watch out, if this does appear on the exam, don't forget to balance the equation such a way with 2 here. And lastly, we're going to say the energy of formation of this reaction is, the enthalpy of formation of this reaction is minus 544 kilojoule. And why did I spend so much time on this table? Is because the very assumption of this table that we can break molecules down into their individual component is we're assuming that the bonds are fully localized. That means breaking a CH bond, no matter the environment, is going to be the same. No matter it's CH4 or it's CH2ClH, this CH bond and this CH bond is completely the same. That is the electron pair and the electron pair here. And of course, we know this is not true. But that's okay. That's our first approximation. That is the localized electron model. Right? We are assuming that electron is fully localized, that it's only going to be centered around 2 atoms. So no matter what changed in the nearby, like having a chlorine here or having another hydrogen here, it doesn't change anything about this electron pair. That is the idea behind localized electron model, LE. Assumes that the molecule is composed of atoms that are bound together by using atomic orbital to share electron pairs, right? So this is going to be a carbon p orbital, and this is going to be a hydrogen h orbital like this, right? So remember, carbon has four orbitals, right? 2s, 3p's, and 4 electrons, of course. And hydrogens are just 1s, right? So we can bond them together to form a molecule like this using the 4 orbitals on carbon, s and 3p's, and then the 4 corresponding 1s orbitals on hydrogen to form 4 bonds. Okay, so to summarize the LE models, there are a few steps. The first thing is description of the valence electron arrangement in the molecule using loose structures, which we'll come back to this. What are loose structures? Which will be a recap for most of you, right? A review for most of you. Prediction of the geometry of a molecule using the valence shell electron pair repulsion. It's called VASPER. Valence, V, shell S, electron S, E, P from pair, and repulsion from R, VSEPR model. It's a really common model that we use in chemistry to predict geometries of molecules. And description of the types of atomic orbitals used by the atom to share electrons to hold lone pairs. I will come back to this. So this might seem abstract for now, but we'll see examples of this. All right. And the first thing we're going to talk about is item 1. Loose structures. So what are loose structures? Right? So the loose structure of a molecule represents the arrangement of valence electrons among the atoms in the molecule. Right? For example, the loose structure only shows valence electrons. Using that to represent the electrons. For example, potassium and bromide. The loose structure for potassium and bromide will look like this. Right? Potassium is going to be nothing. Bromide is going to be 8 dots. And it's not just randomly dotting 8 dots around bromine, but they are supposed to form pairs, right? So you're going to see two dots forming a pair on one side, 2 dots forming a pair on the other side, and 2 dots forming a pair on this side, and 2 dots forming a pair on this side. And this is called a loose structure of bromide, a loose structure of bromide. And just by looking at this loose structure, we immediately know as a chemist, this bromine is minus charge. It's minus charge. And this potassium is plus charge. It's plus charge. Why? Because if you look at the periodicity table, you realize bromine is in the halogen group, right? Chlorine, chlorine, bromine is in the fourth row. That means it must have 7 valence electrons, but if you check out the loose structure, you realize there are actually totally 8 electrons dotted. Okay, and that means the bromine has 1 more electron than its valence shell, in its valence shell, hence it's going to be minus charge. It's going to be the same story for potassium. Potassium is going to be in the 1A with hydrogen, lithium, potassium, right? Sodium, potassium. So it's going to be again on the 4th row, and it's going to has 1 valence electron. And just by looking at loose structure, you realize there are no electrons surrounding that potassium. That means the potassium had lost one electron, right, before we even started the loose structure. So this already implies two things. The first thing is the charge. Just by looking at the loose structure, you know the charge. The second thing is you know how many lone pairs and how the electrons pair together, right? For potassium, there will be no valence electron, For bromide, there will be going to be 4 pairs of lone pair electrons. 4 pairs of lone pair electrons. Any question here? All right, should be a recap. And this should be, if this is not familiar to you, please review this because this should be kind of like a really fast response. Okay, and I kind of went through this, right? So we're not going to go through this, right? And of course, for the whole periodic table, then we can come up with rules, right? So for metals, right, the part of the periodic table that they have lower electronegativity, again, go back to Linus Pauling's electronegativity, they will lose their valence electrons because they have low electronegativity, right? So for alkaline metals, if you draw their loose structure, you immediately know they are 1 plus charge. For alkaline earth metal, if you draw their loose structures, you know they are 2 plus charge. For the 3As, 3 plus charge. 4As, hard to say, right? Because 4As right now get into non-metal or metalloids, right? Then they could be negative, they could be positive. Loose structure are harder to define, right? And for 5A, 6A, and 7A, pycnogens, halogens, chalcogens, and halogens, they are negative charge. So you expect to see what? To see they are going to have a loose structure look like this. They're going to have an oxygen here with 4 pairs of lone pair electrons, and implying that it's 2 minus charge. It's a nitrogen again, and will be 4 pairs of lone pair electrons, implying it's 3 minus charge. Okay. So basically, what you do is you're going to take this number, subtract it out by 8. Take this number, subtract out by 8. So 5 minus 8 is minus 3. 6 minus 8 is minus 2. 7 minus 8 is minus 1. On the other hand, it directly takes this number and add a plus sign to it, right? 1 plus, 2 plus, and maybe 3 plus. Boron is not really a metal, right? It's a metalloid. And this can be understood just by looking at the electronegativity table that usually, right, what we cut is around here. Right, so everything here, so you can see that everything below 2 will be positively charged. So aluminum is going to be 3 plus, it's in 3A, gallium 3 plus, indium 3 plus, beryllium 2 plus, etc. And on the other hand, greater than 2 or around 2, these are metalloids, right? Semi-metals. Those are hard to define. And those around 2, beyond 2, higher than 2.5 are negatively charged. 4 minus, 3 minus, 2 minus, 1 minus. Right, so again, the ones having higher electronegativity values, you take their row, their column number, subtract out by 8. Right, so 4 minus 8, 5 minus 8. The ones smaller than 2 will be the positively charged. You take their column number, group number, and directly add a plus sign to it. And you can draw the loose structure correspondingly. Any questions here? Okay, I'm a little bit fast here, so if you don't follow, that's okay. Just raise your hand, and I'll try to explain again. And we're going to see a lot of examples here, right? Because this is kind of the common language for chemists, so you kind of really need to know the language here in order for us to actually communicate. All right. So loose structures, the ones we just learned are for ionic compounds. One completely loose electron, one completely loose gain electrons. And why? Because they have a drastic difference in electronegativity. But what if you have 2 elements that have similar electronegativity? They form covalent bonds, right? So we're going to learn how to draw loose structures for covalent bonds, or covalent compounds. They share electrons, and each hydrogen, for example, has 2 electrons. This gives electric field valence shell, something like this, right? H dot and H dot will form HH dot dot. So to draw the Lewis structure for hydrogen, H2, what you have is HH and 2 dots in between. And again, when dots are in pairs, implies either they are bonding electron pairs, if they are shared in between 2 atoms, or they are lone pairs, if they are only centered around one single element. Okay, And the goal of sharing is such that it to fulfill its valence shell. For hydrogen, it's just going to be 1s. So 2 electrons, this hydrogen fulfill its valence shell, and the other hydrogen is the same, fulfill its valence shell. For example, for fluorine, another example, each fluorine atom has 3 pairs of electrons not involved in bonding. Fluorine is in the 7A, right? So to draw the valence structure for fluorine atom, it's going to look like this: 2 dots, 2 dots, and 2 dots. That means this fluorine has 3 lone paired electrons, 3 lone pairs of electrons. And the last one is called unpaired electron. 所以这就是成对电子跟不成对电子。And right now, this fluorine is bonding to the second fluorine, and the goal is to fulfill what? Its valence shell. So the way to fulfill its valence shell is to share that 1 electron. So 1 electron coming from this fluorine, and the second electron coming from this fluorine. Oh, I forgot to change this into duplicate slide. Okay? Yeah. Okay. And this way, just by counting all the electrons surrounding this fluorine, you're going to see 2 dots, 2 dots, 2 dots, and 2 dots. So this fluorine right now has all its valence shell filled. The same for the other fluorine. And they share 1 electron pair. And this is the correct Lewis structure for fluorine atom. Okay. And neon, of course, the noble gas don't really need to share, so does not form bonds since it already has an octet of valence electrons. 2, 4, 6, 8. Right. And by octet, we mean that it fulfills all its 2s2p shells, right? Or 3s3p, 4s4p. That means there are 8 electrons in its valence shell. Okay, so previously we just learned about how to draw the Lewis structure for ionic compounds. Right? For the metals, it's going to be no electrons surrounding the element. For non-metals, it's going to be all electrons surrounding its element. And typically, it's 4 pairs of valence electrons. And on the other hand, for covalent compounds, they do it by sharing electrons. And the goal is such that when you actually look at the element will be surrounded by 4 pairs of lone pair electrons. 4 pairs of electrons. So, sorry, 3 are lone pairs, and 2. In this case, 3 are lone pairs, and 1 is a bonding pair. All right. So just summing up this, right? And then we're going to come to examples for you to do, and of course, I'll ask for volunteers. That is, to write a Lewis structure or to write Lewis structures, count the valence electrons from all the atoms. And do not worry about keeping track of which electrons come from which atoms. This is the total number of electrons, not important. For example, fluorine will have 7, the other fluorine will have 7, so totally 14 electrons. Use a pair of electrons to form a bond between each pair of bound atoms. So you're going to use fluorine, and fluorine is going to put 2 dots in between. Actually, let me do this. Okay, let's do it together. So the first rule will be clear F. So number of valence electrons per F is 7, and we have 2 times 7 is 14. Okay, so that's rule 1. Sum up all the valence electrons from all atoms. And of course, this is a simple case. You can go to really large molecules. Right, large molecules. And now you form pair. Right. So the second rule is use a pair of electrons to form a bond between each pair of bonded atoms. So in this case, it will be FF, and you put a bonding pair in between. I'm only drawing this for you to see, right? This shouldn't be drawn. Okay? And then arrange the remaining electrons to satisfy the duet rule for hydrogen. So hydrogen only has 1s orbital, right? Only need 2 electrons, and octet rule for the second row elements. Okay? So we used 2 electrons, so 14 minus 2, we have 12 electrons left. Now what you do is you put pairs of electrons surrounding the element such that each element has totally 4 pairs of electrons surrounding it. 2, 4, 6. Now this fluorine is happy, right? Because it has 1, 2, 3, 4 pairs of electrons surrounding it. 2 are lone pairs, and 1 is a bonding pair. So that means we take 12, and then we just use up 3 pairs minus 6. So we have 6 left. Right? And the other one the same for fluorine. Right, 1, 2, 3. So again, 6 minus 6 equals 0. Okay. Now we are done. But of course, you might wonder, what if we cannot really finish the rule? What if we only have 4 electrons left here? Right. So what if we somehow we lose 2 electrons? Then we need to have 2 bonds. Right? All right. So just look at some examples here, and then later on it's going to be your turn. Example 1, for example, water. That is, we have somehow the valence electrons for H2O. Hydrogen and hydrogen each have 1s, 1s, and the oxygen is in the second row, and it's in the 6A chalcogen groups. So it has 6 valence electrons. It has total 8 electrons, but 2 are core electrons. 1 plus 1 plus 6, so total we have 8 valence electrons. The second rule is use 1 pair of electrons per bond. We draw the 2 OH bonds, right? It could be HOH, it could be HHO, OHH. And of course, we know what makes sense is to put the most electronegative element in the middle and to put the less electronegative elements in the neighbors. HHO and then pairs like this, right? HHO pairs. And we are kind of lazy here while drawing a bond instead of 2 electron pair as a pair. Okay? And note that the line instead of a pair of dots is used to indicate each bond of bonding, like each pair of bonding electrons. And lastly, we use 2 electrons and 2 electrons, so we take 8 subtracted by 4 because 2 pairs here. So we have 4 electrons left. And of course, naturally, what we're going to do is we're going to distribute the remaining electrons around the atom to achieve a no-gas electron configuration for each atom. So we put 2 electrons here and 2 electrons here. Then you complete the Lewis structure for H2O. That is HHO, bonding pair, 2 lone pairs. And we use up all the 8 electrons. And if we double check, the hydrogen right now has fulfilled the duet rule, 2 electrons. The other hydrogen fulfilled the duet rule, 2 electrons. Oxygen, 2 electrons, 2 bond pair, 1 bond pair, and the second bond pair. So 8 electrons. Duet, and octet rules. Any questions here? Should be easy. Okay, that's good. And the second one is more complicated. As I mentioned, what if we don't have enough electrons to fulfill the octet rule? Then we need to share by more than 1 pair. Right? That is when we need more sharings. So for example, carbon dioxide is a really good example. We just do the same thing. First, total number of electrons, oxygen is 6, hydrogen is 4, oxygen is 6. So 4 plus 6 plus 6, we have 16 electrons. Okay, and second one is the octet rule for each element. And we're going to fulfill the more electronegative element first. Because they are more electronegative, they can hold the electrons stronger than the less electronegative elements. So what we're going to do is something like this, right? 2, 4, 6. 2, 4, 6. Right? Because 1 bonding pair, 3 lone pairs. 1 bonding pair, 3 lone pairs. And if we count the electrons, 2, 4, 6, 8, 10, 12. So we just used up 12 electrons. In addition, we have 2 bonding pairs. So 14, 16. That means we use up all the valence electrons. But if you look at this structure, it's not correct because carbon only has 2 bonding pairs. That means it only has 4 valence electrons. This is not true, right? So what we're going to do now is take this structure and then we share electrons, right? What we can do is instead of oxygen having its own lone pair, we're going to bend this electron down such that it's shared between carbons like this. And it's going to be the same, the other side. By doing this, you do not change the amount of the number of valence electrons that oxygen has. Right, check this out. This oxygen, before sharing its lone pair, has 2, 4, 6, 8. After sharing its lone pair, 2, 4, 6, 8. So sharing a lone pair does not change the number of valence electrons this element has. Okay? I'm just going to recap one more time. So this oxygen, right now we are sharing. Why? Because by using up these 16 electrons, we cannot fulfill the carbon's requirement to have 8 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16. So right now we are forcing the oxygen to share electron, and by sharing electrons, oxygen does not lose its octet rule. Right? 2, 4, 6, 8, 3 lone pair and 1 bonding pair. And here oxygen share 2 lone pairs as bonding pair, right? So 2 bonding pair, 2 lone pair. It still has 8 valence electrons. So by sharing electrons, the element does not lose its octet rule, but it helps the other element to fulfill its octet rule. By sharing, the carbon right now fills 2 bonding pairs, and the other side fills 2 bonding pairs. So carbon right now fulfills its valence electrons, the octet rule. Right. So this is one way to fulfill octet rule. That is by sharing electrons. Any questions here? Right. And I think it will be your turn to do it. And there's another cyanide. Let's quickly go through this because cyanide is a tricky one. That is, it has odd number of valence electrons. Right. So again, the same rule, right? So by drawing a single, if you count the valence electron for carbon, it's going to be 4. Valence electron for nitrogen is going to be 5. That means it only has 9 electrons. And it's not possible for 9 to be divided by 2 without reminders, right? It's going to have 1 electron left. So what we're going to do is we can add 1 electron through minus charge, or we can remove 1 electron through plus charge. In this case, we add 1 electron with a minus charge. So 4 plus 5 plus the minus charge, you get 10 valence electrons. And again, draw a single bond, you're going to get something like this. 1 electron pair, 2 electron pair, 3 electron pair, 4 electron pairs, and 1 bound electrons use up the 10 electrons. And of course, none of these elements fulfill its octet rule. So right now we're going to bring down. And which one are we going to bring down first? From lone pair to bonding pair. We're going to share the less electronegative one first, right? So carbon will get bring down. Now carbon has 2 fourths. Let me draw it. It's a bit easy for you to picture this. Okay. So originally we have this. 2, 4, 6, 8, 10. So we use up all the 10 valence electrons. And right now, of course, none of this fulfills octet rule. Because if you do the counting for carbon, 2, 4, 6. Do the counting for nitrogen, 2, 4, 6. So right now we're going to share. Which one to share first? We're going to share from the less electronegative part. So we're going to move it such that this pair gets moved down. And if you do the counting, you realize this carbon has 2, 4, 6 valence electron. This nitrogen has 2, 4, 6, 8 valence electron. And of course, minus charge. And this nitrogen is happy because carbon shared electron with it. But this carbon is not happy yet. So of course, now we bring the other lone pair down. So it's going to be 3-4 bounded, minus charge. And now you do a counting. 2, 4, 6, 8, 2, 4, 6, 8. So 8 valence electron, 8 valence electron. And this is the correct Lewis structure for cyanide. The molecule is called cyanide. 中文应该叫氰化物吧？对，就名侦柯南每次杀人用的。好 ，Okay. And you quickly realize one thing. That is something I say is not consistent. That is, when we share electron, we move the lone pair on the less electronegative side first, then the more electronegative side first. But if we go back to carbon dioxide, you realize we share the one on oxygen first. Why? Because carbon didn't have any lone pair to start with. Right? It doesn't have lone pair to share. Okay, so that's a rule, right? So the first thing you do is sum up all the valence electrons to make sure how many electrons in total you can actually distribute in bonding pairs, in lone pairs. And the second is you put elements, the most electronegative in the middle, and in this case it's kind of symmetric, so it's really hard to put it in the middle. Okay, and what you do is you form single bonds, and then you give electrons in as lone pairs to the more electronegative side first, and then less electronegative side first. And when you run out of electrons, all the valence electrons, but you still have elements that does not fulfill valence octet rule, then you start to move lone pair down, becoming bonding pairs, which does not change the amount of valence electrons that particular element has, but increase the valence electrons count of the surrounding element. And that is called sharing an electron pair. Okay, any questions here? And I think it's your turn. Okay, this is resonance structures. I'm going to let you draw out the Lewis structure for these 4 first, and I'm going to ask for volunteers. Then we'll come back to resonance structure, and we'll come back to this question to understand what are resonance structures. All right. 好，那这部分我让你们先试一下哈，因为刚才讲了一堆，就是我们现在有4个 molecule， 那请你们把它们的 Lewis structure 画出来。那当然，我等一下一样会问一个 volunteer， 这是算那个 attendance point 的部分。如果你之前刚好有课没有跟上，或者点名没有点到的话，那这个部分可以帮助你把 attendance point 赚回来。然后等一下我们会再讨论什么叫做 resonance structure， 用这4个当 example。So now it's your turn to actually draw the Lewis structure for these 4 molecules. One more minute. 再1分钟哦。 Okay. All right. Any volunteers?好，那如果没有的话，我就自己做了。哦 ，OK。好，可以。可以。好，没有错哦。That's right. So a few things. 好，同意他是对的吗 ？I guess agree that he was right. Is what you got? 你们也是找到这样答案吗？那我觉得很好，这个画的都对。那等一下就是有几个部分要讲，就是我们等一下会讲的 reason structure 跟 formal structure 的部分。好，那 so the first thing that you quickly realize, and of course he was completely right, but there are some things that I didn't teach you yet. That is, if you look at this structure, and if you look at this nitrogen here, and you realize this nitrogen fulfills its octet rule, right? So if you count this part. 2, 4, 6, 8 valence electrons. But if you look closer, you realize that if we think about forming a bond or covalent bond is by sharing an electron pair. What does that mean? That means this pair of electrons really comes from a dot from nitrogen and a dot from carbon. Right, we share a pair of electrons. So if we count back as before we even drew the bond, you realize that means this nitrogen had how many electrons? Half. That means this nitrogen only has 4 valence electrons. And is this correct? How many valence electrons should nitrogen have? 5个嘛，对不对？所以那这不对啊，那颗电子跑去哪里？没问题哦，这个结构是对的，但是那个东西我们叫它 formal charge。formal charge。所以实际上在化学上我们会再多做一步，没关系，那是因为我还没教，所以你们不知道是应该的，就是我们会 put a positive charge。To actually say that this nitrogen actually lost one of its valence electron in order to accommodate 4 bonds. Right? Originally, in order for nitrogen to have octet rule and to fulfill the number of valence electrons, it should be like this. Right? So 1, 2, 3, 4. Right? So 1, 2, 3, 4, 5. But in order to form the 4th bond with oxygen, right now you need to give out both of its electrons to form a bond. In this case, it lost one of its valence electron. Hence, the formal charge on that nitrogen is right now positively charged. And the same for this oxygen, right? If you look closer again, you realize he has 2, 4, 6, and then one more electron from sharing. So he has 7 valence electrons, while oxygen should only have 6. That means this oxygen gains one more electron, so its formal charge will be minus charged. So it's going to be plus and minus, and this whole molecule is also neutral. 好，这部分有听懂吗？这个东西叫做 formal charge。等一下我们会看 example 哦，不用担心。如果现在觉得，老师你这样讲我还是没有听懂，没关系，我们等一下再讲电话。这个 how we call this are called formal charge。那 formal charge 是一个蛮重要的 concept， 原因是为什么呢？是因为实质上在我们身体里面有很多的氨，有很多的 ammonia 哦，你的蛋白质里面基本上都是氨哦。然后甚至还有很多什么，我们身体里面也含有大量的像 urea， 比如说像尿素，它也都是含有氨。也就是说，这些氨实际上是碱性的。我们这堂课不讲酸碱，它是碱性的。所以当它得到一个 proton 的时候，它的 formal charge， 它的 charge 实际上会变正。那这时候这个氨是什么？它是一个酸，它是一个路易斯酸。所以 formal charge 越 positive 的 element 实际上越像路易斯酸。That's a lot of things, but that's what I will explain. On the other hand, it's going to be the same, right? This oxygen has a formal charge of minus charge. That means it's going to be a really strong Lewis space. 好，那我这堂课不讲酸碱哦，大家大概理解一下就可以了。好，那一样，从这里也是一样的。The same is going to apply here, right? So if you look at this nitrogen, 1, 2, 3, 4. So every sharing of electron means one element will give one electron, the other element will give one electron. So if we move back to elemental form, this nitrogen will get this electron. This nitrogen will get this electron. This nitrogen will get this electron. This nitrogen should get this electron. And this is what we call homolytic cleavage. But you don't need to know that word, homolytic cleavage. Or equal sharing of electron. Again, this nitrogen means it has one less electron, one fewer electron from its valence shell. So it's going to be positively charged. This oxygen will be okay because 2, 4, 6. And it's similar, it's the same to its column, right? 6A. For this oxygen, 2, 4, 6, 7. 2, 4, 6, 7. So that means we're going to apply one minus formal charge for this oxygen, another formal charge for this oxygen. And if we sum up the charge, minus 1, minus 2, plus 1, it makes sense because the overall molecule is negative. Right? So it's negatively charged. And hence, this is actually an ion, right? An anion. 一个阴离子，一个阴离子，一个 anion. Okay? And this makes sense because previously we didn't have any charge on this molecule, so the molecule wasn't actually had the correct charge as the whole ion. Okay? Any questions here? And of course, we can do the same trick, right? It's going to be the same here. This nitrogen, 2, 4, 5. So it's okay. So it's 0. I'm just writing 0 for bookkeeping. It's going to be 2, 4, 6. So 0. And this oxygen, 2, 4, 6, 7 minus. Right? So the formal charge on this oxygen will be minus charge. And that makes sense, NO2 minus. And so this is nitrite. This is called nitrate. And this is called nitrate. Okay. And you don't need to know the name. Don't worry. 这个叫硝酸吧，这叫亚硝酸，硝酸盐跟亚硝酸盐就是硝酸跟亚硝酸。好 ，you don't need to repeat it. Can write it. 好，然后最后一个一样，我们把它 fulfill 哦，就是 the last one. Right. So nitrogen, 1, 2, 3, 4, 5. So it's okay. And oxygen, it's 1, 2, 3, 4, 5, 6. It's okay. And carbon, of course, is okay. Alright? Any questions here? 没事哦，如果你刚出错了，不用担心，就现在答案其实也都在后面了。So answers are at the back. So you can see that I purposely, when I drew this molecule, I put a negative charge, positive charge here, negative charge here. And sometimes you can put like a circle around, or sometimes you can put plus, it doesn't really matter. It's the same for this molecule. Nitrogen plus, minus, minus, and plus, minus, minus, plus, minus, minus. And these three are called resonance structures. We'll come back. And then again, this nitrogen, this NO2 will have a minus charge here. And lastly, this doesn't have any 4 more charges here. And this is called 4 more charge. 4 more charge. Okay. Any questions? 好，那如果说刚才没有跟上的同学，没关系，回去再把 slides 看一下哈。那至少这4个分子要知道怎么画。那它应该算是，它也比较难啊，所以就要故意选这4个分子，就是因为它们真的比较难。所以你画错也没有关系，这是应该的。那尽量看一下有没有办法，就是多做几次，看能不能把它画对。好，那实质上上面这个分子为什么故意选这个分子？这个分子是一个很有趣的分子哦，它叫做amine oxide。amine oxide。那 amine oxide 是什么呢 ？amine oxide 是实质上，如果这里有化学系或化工系的同学，之后会用到化学品的，你们就会知道任何胺类的盐实际上都是不稳定的。So let me show you in English. So if you happen to be in the future, if you happen to be using any chemicals, you realize that amine-based compounds are really not stable. And why? Because they can get spontaneously oxidized by oxygen. 所以实质上胺类的盐在空气中它是会被氧化的。所以胺类的盐一般我们要怎么样？要么把它放冰箱，把反应速率下降。那我们后面会提到，等我们学 entropy 的时候，我们会学反应速率跟这个温度之间关系是什么。第二个是什么？要么就是把它放在没有氧气的地方，比如说如果你们组有手套箱啊，所以你就把它放到手套箱。为什么呢？是因为当它变成了氧化物的时候，它其实是非常不稳定的，它是有可能爆炸的。So ammonia oxides are actually potentially explosive. Why? Because this nitrogen really doesn't want to be positive. So what will happen is anything in the surrounding is going to react with that molecule. And remember, this is a bottle of ammonia, bottle of amine, nitrogen-based compounds. So the first thing this oxygen will do is to react with the methyl group in the surrounding molecule. This can polymerize, can actually create a lot of heat, and this thing can actually explode if it's in large quantity. And of course, it's not going to be in large quantity. And how do you know? 你怎么有办法知道是不是这样的结果呢？这个东西一般是有颜色的哈 ，amine oxide 一般是有颜色的。那这个部分就多讲一些啦，就是实际上化学其实有很多比我们想象中还要复杂的地方，因为空气中很多大量的氧气。好，那最后我们要再回去讲一个东西，就是刚才没有讲的，就是这3个结构。So if you look closer, you realize this nitrate can potentially have 3 forms. That is double bond bonded to this oxygen on the upper left, double bond with this oxygen on the upper right, and double bond with this oxygen at the bottom. And you quickly look at these structures, 3 structures, you realize none of them is wrong. And the reality is none of them is also right. 所以实际上这3个结构没有人是对的，但是也没有人是错的。这就是一个很有趣的结构哈。比如说我举个例子，这个用这个颜色有点不容易看。So if you actually look at the number here, it's a little bit hard to see. Let me draw it out for you. That is, for nitrate, we can actually draw 3 potential loose structures, and they are all correct. That is, we can give the double bond to different places, right? We can have double bond here. And put the 4 more charges, and again. And these are called resonance structures. I'll come back to the previous slide to talk about them. And which one is right? The answer is none of them is right. The reality is it really should be something more like this. That is, the second bonding pair should really be delocalized throughout the structure. That means these 2 electrons should be shared by these 4 atoms. And how do we know this? This is the real bond distances from crystal structure. 记得吗？自从我们知道了 X-ray diffraction 之后我们学 bonding solids 跟 liquid 之后，我会讲稍微提一点点哦，但这样其实不需要知道。那 we can actually do X-ray diffraction, so we can really take nitrate and see how do we look like. And if you take a closer look, the color is really hard to see. It's about 1.251, 1.245, 1.248. So we can actually directly look at the molecule and ask how long are your bonds, and you quickly realize the bond length is this. They are very close to each other. 也就是说，如果说他们是 double bond 跟 single bond， 我们要看到的是有一个会特别短，有两个特别长。但是实际上我们看到的不是这样。实验上我们真的把实验做出来，发现三个 bond length 差不多。你说这个稍微长一点，那因为这个是 counter A9， 对不对？所以代表我们一定会有一个 K 台，比如说 Q10 在这边，它会形成类似 bonding， ionic bond。所以实质上我们 draw 这些 resonance structure 只是为了，因为我们方便，人类需要这样的图片方便。但是实际上真的在分子里面并没有真的这样的一个三个结构在那边 switch 来 switch 去，这个 bonding pair 实际上是像一个 electron cloud 一样在里面一直在 rotate 在 rotate 在 rotate。你可以把它想看它是一个2-dimensional particle in a box， 然后这个 potential 就是像一个冰室的形状的 potential， 然后这个 electron 被 confine 在里面，你就会想象这个 wave 会长得很奇怪，但是没关系，大致上想象成那样就可以了。所以它会是一个 2-dimensional 的 particle in a box， 那这个 electron pair 就被 confine 在这4个 atom 里面。好 ，OK， 只是给大家一个概念啊，就是 resonance structure 存在，那是因为我们化学家需要画这样的图，它看起来方便，但实际上它并不是真实的存在。真实的存在应该是像这样，就是大家各有一个 electron pair， 然后接下来剩下的那个 electron shared by 4 elements。And of course, double bond do exist. 在没有 resonance structure 的情况下 ，double bond 是真实存在的。